Hey everyone, I'm going to go ahead and record the solution to your homework. Marker here. That arrow out of the way. Alright, so I think we're ready. Zoom out just a touch. Okay, well, I think I'm stuck with what I've got. Alright, let's go ahead and maybe if I just lift it up, I can see a little bit more. Alright, so sorry about that. It's just trying to get things situated right. Alright, so this is the key to our second exam. I'm going to go ahead and discuss the rubric at the start of next lecture, because there might be some questions about that. Alright, so the first question is here. We have the sliding and spinning dumbbell question. And of course there were some people who wanted to do the exact question from the lecture demonstration, but it is an exam, so there's going to be tweaks, and maybe I'll ask for something slightly different outcomes. So that's something to look for on future exams. Too. Sliding and spinning dumbbell. A dumbbell consists of a massless rod with two uniform spheres at the ends. We're going to give each of those spheres a mass of m, okay, just to be consistent for all of us. At t equals 0, the left mass is given a sharp tap with a force with magnitude F in the y-hat direction. The tap lasts a very short time, which we're calling that amount of time that the tap lasts delta t. What are the velocity of the center of mass of the dumbbell and angular velocity of the dumbbell as functions of time during the short tap? Okay. What are the locations of the center of mass and angular displacement of the dumbbell as functions of time during the tap? And lastly, what are the velocity of the center of mass of the dumbbell as angular what are the velocity of the center of mass of the dumbbell and the angular velocity of the dumbbell as functions of time after the tap? Alright, so I'll go ahead and do a solution here. Alright, so first thing I was told in class was that I must have a figure. And the reason why I must have a figure is because I must have a coordinate system. And the easiest coordinate system for the solution here is this one. So I'm going to call this the x direction, that the y direction, which is similar to the class example. As a result of that, that means that out of the page is the z hat direction. Obviously there's the origin, so the z hat direction is coming up out of there. Okay, so in this case what's going to happen is at t equals 0, I'm going to begin to feel a force F acting on the left sphere. And here I need to also define how I'm going to describe the length of this dumbbell. I'm going with from the center of mass of the left object, or the right object since there's symmetry, to the center of mass of the overall object, the center of mass of the dumbbell. I'm calling that distance L. Okay, so there's my figure. So for part A, so the question asks about the velocity of the center of mass of the dumbbell as a function of time during the tap. So I take any arbitrary time and I will call that the final time. Oops, plus. Let me shut off that. Hold on just a second. How do I close that? Here we go. Get rid of that. Good. Okay. So plus F external dot or times dt. And this guy here is called the impulse momentum theorem. Remember, whenever we do something that involves a physics law or definition, we have to name it. And obviously starting points always pretty much need a name. Alright, so in this case, this is a vector equation, but I know only the y component portion of this equation will be non-trivial, so I've got py, and what I'm calling final is just at some time t during the tap, and that's equal to p initial y, where I'm going to call t equals 0, where this force acts, so initially it's at rest. So plus the force whose magnitude, whose y component is just f, and the time, it is a constant, so it can come out front of the integral, and the time elapsed is t, not delta t, because I'm during the tap, so t must be less than delta t. Okay. So for my expression for y component of momentum of my dumbbell, it's the total mass of my system, which is 2m. Each of these has a mass of m, and it's a massless rod. So Vy of the center of mass so I've got F over 2m times t. That's my velocity of my center of mass as a function of time during the tap. Next, I also needed to find the angular velocity. And so this was the angular analog to the impulse momentum theorem. You could also get it from the definition of torque, or Newton's second law for rotation also. All of that would work. Okay. So in this case, the only component, because this object is going to begin rotating about this direction. And velocity and angular momentum, which you were asked about here, are vector quantities. So, I'm sorry, angular velocity was that word. Both of those are vector quantities, so they must have some direction information in their answer. So clearly here I have direction information in my y subscript. All the others are 0. If you want, we can also do this. That's fine as well. Okay, so I need to do the same thing here, meaning I need to have a direction associated with it. So I'll notice that the only non-zero component of angular velocity for this object will be about the z-axis direction, because it's going to tend to rotate like this. Come on, camera. The camera on my screen is frozen. I don't know about you guys. But it's going to tend to rotate like this. So that's associated with rotations about the z-axis. Alright, so I've got L final about the z-axis. And yeah, I can just note that's just L as a function of time. Okay, because I'm having the final be at some time t, where t is less than delta t. And that's equal to 0 because it was initially at rest. Plus the torque, which is also going to be associated with this force. And so I'm going to, by the way, whenever you do angular momentum, you have to choose a point about which you are calculating it. So I'm going to be very clear here and say I'm going to do this about the center of mass of my dumbbell. In that case, the torque is going to be having a magnitude of F times L, and it is tending to torque the object this way. So that's about the negative z direction. Since I want z components here, I need a minus sign there. Okay. And so it's going to stay constant, so I can pull that out front, and that gives me an integral which is just a product of the two. Okay. So now I think I'm ready to solve. Lz as a function of time is equal to minus, oh, you know what? I didn't want Lz. I wanted omega z. That's right. So let's go ahead and note that for Lz, that's going to be equal to I times omega z, where the rotational inertia of this object, well, I can treat both of these objects, these spheres, as point particles located at their centers of mass. So I'm going to have an ml squared associated with the left sphere, because I can go ahead and use my expression there for a point particle, because it's an extended object, We did that proof in class. So that. And then also I'll need to add the angular momentum of the right hand side, which I could just put a 2 in there, and the rod itself was massless. So okay, so I'm going to go ahead and make that substitution here. Let's go ahead and do that. So LZ is a function of time, which will be I times omega, so 2mL squared times omega z as a function of time, equal to minus FLT. All right, so omega z as a function of time must be equal to minus F, I'm going to cancel that with that squared there, okay, over 2mL times T. Okay, so that's the answer to part A. Now for the answer to part B. What are the locations of the center of mass and angular displacement of the dumbbell as functions of time during the tap? So that means both of these hold for t less than delta t. And by the way, if I wanted to make that a vector expression, just put a z hat there. So both of these are during the tap. T is less than delta t. Okay. So now, by the way, I'll just show what I did there. Okay. All right. So then for part B, I want to know location as a function of time during the tap, and that's location of the center of mass. So for that, I'm going to remember that initially in my I defined my coordinate system such that its initial location was at the origin, so y was 0, and its x and z components of that location are going to remain 0, so the only non-trivial one is y as a function of time, and we should remember that y at t equals 0 was defined as 0. And to solve this problem, I'm just going to use the definition of velocity. Okay. Alright, so let's go ahead and do that. I feel like that's a little too tippy, so let me see if I can get that there. Alright. Alright. So, we'll just multiply both sides by dt and integrate, and that gives me, let's I multiply both sides by dt, that gives me dy is equal to vy dt, which I'm going to integrate from initial to final, which will be from 0 to some later time t, where t is less than delta t. And dy also started out at 0 and will wind up with its value at t. Alright, so obviously on the left hand side I get y, which I must evaluate from 0 to y of t, which gives me y of t. And on the right hand side I've got vy, which I solved for in part A, so I'm going to go ahead and make that substitution. F over 2m are all constants. Pull that out front. The integral of t dt is t squared over 2. So I'll get f over 4m t squared. So location of the center of mass as a function of time is f over 4m t squared in the y hat direction. That's my answer, and this holds for t less than delta t. Okay, I also needed to find the angular orientation as a function of time. So for that I will use omega z is equal to d theta dt, where theta will be defined as usual, the angle with respect to the x-axis. Sorry, I'm going to try to show you that. Where those will be positive thetas, these will be negative thetas. And it was fine if you wanted to use phi's. That would actually make more sense to use a phi, but I used a theta, so I'm going to stick with it. Alright, and this is from definition of, in this case just omega z, multiply both sides by dt and integrate. So I will get d theta is equal to omega z dt. And time is going to go from 0 to t. Theta is going to go, its original orientation is when the right mass lies on the x-axis, so I'm calling that theta equals 0. So it's initially at theta equals 0, and it will go to theta at time t. Alright, so obviously on the left-hand side I'm integrating d theta, which just gives me theta, which I must evaluate from 0 to theta t. So I get theta t. And that must be equal to the right-hand side. I'm going to go ahead and make that substitution. 0 to t. Omega z component is what I solved for in part A, and I got negative f over 2ml times t dt. And so I've got negative f over 2ml are all constants I can pull out front. The integral of t dt is t squared over 2, which I must evaluate from 0 to t. Okay. So I've got negative f over 4ml t squared. So in that case, I'd say theta as a function of time, if I want to express it as a vector, is equal to this rotation about the z-axis, and that's all. Okay. All right. So let's go ahead then and talk about part C. It's a question for part C. What are the velocity of the center of mass of the dumbbell and the angular velocity of the dumbbell as a function of times after the tap? Oh, right. Well, after the tap, there's no longer any force and there's no longer any torque. So the velocity will continue to be its expression from here. You just have to evaluate that at delta t. And omega t will be equal to about the z-axis, and this will hold for after the tap when t is greater than delta t. Okay? All right, so I think that's about all. Well, I guess if you wanted to, you could also go one step further. This isn't part of the test, but I just wanted to clarify that what this means is that y, the location of the center of mass as a function of time then, will be equal to its location at delta t. So that's at the end of the tap, so I'm going to use this expression right here for that. Plus, however far it moves afterwards, in which case it's moving with this constant velocity. So it would be f over 2m delta t times how much time has elapsed since it started moving like that, which is t minus delta t. And there's some algebraic simplification you could do there if you wanted to. I think the final expression I got, just for grins, remember we're not answering any part of the question here, I'm just sort of showing what you can do with this. F over 4m delta t times 2t minus delta t. If you want to do some algebraic simplification there. But anyway, so now what this tells you is that we have truly solved the motion of this object because we know where its center of mass will be as a function of time. And similarly, we know what its orientation about the z-axis will be as a function of time. So go ahead and write that in symbols. So it's going to be whatever its value is during the tap. So remember, this is during the tap, so this is where t is less than delta t. So at the end of the tap, I just need to plug in delta t for t. And then I need to consider that after that time, it proceeded with this constant angular velocity, so minus f over 2ml time elapsed. Oh, by the way, I need my delta t there. Time elapsed while it moved that way, which is t minus delta t. And I can also simplify that one with some algebra if I want to, and I get negative f over 4ml delta t times the quantity 2t minus delta t. So I have indeed solved this extended object because I know where the location of its center of mass will be at all times, and I know where it's, this is obviously before the tap is over, it's here, and after the tap is over, this is the expression we would use. And notice that they're continuous because at the time that the tap ends, they're equal to each other. Alright, so I've solved for the location of the center of mass as a function of time and the angular orientation of that object as a function of time for all times. So I've solved for its motion. Okay. And yeah, that was not the identical question to the lecture example, and as well I didn't want it to be, because the point is not that one would rote memorize something, but the point is that I want to ask a question about a system, just like before, where it's slightly different, it is somewhat different, and I can see you doing physics in real time during the test instead of, So I know if you're wondering why wasn't it the exact same question, it's because I didn't want you guys memorizing, I just wanted you doing physics in a problem with which you were already familiar. Okay, so I'm going to go ahead then and start with number 2, but I need a little drink of water, so let me pause this for a moment, and then I'll